Theia hit at an oblique angle, causing the Earth to spin faster, and debris from both Theia and the Earth to fly into orbit. When the dust settled, the debris began to coalesce in Earth orbit, forming the Moon. By then, volatile compounds like water had evaporated. The Moon then comes primarily from the mantles of the Earth and Theia. That's why overall, the Moon is lighter or less dense than Earth. It has a core of solid iron like Earth, but this core is relatively small compared to ours. From this violent beginning, the Moon gradually cooled, and the magma that lined its surface hardened into a crust. Yet it was still subject to intense bombardment in the chaotic environment of the early solar system. Its surface has been hammered by large impacts at every street. You can see what a battering the Moon has taken in this global elevation map compiled by the Lunar Reconnaissance Orbiter. The Apollo astronauts encountered a secondary effect of all the impacts. Rocks formed in the crucible of widespread volcanism. On Earth, volcanic eruptions are often powered by water, heated and pressurized by friction from the movement of immense tectonic plates. Neither factor exists on the Moon. Instead, lunar volcanoes are tied to impacts forceful enough to melt the surface and release material from the hot interior. In the lower gravity of the Moon, volcanic eruptions would have splattered high above the landscape. Molten rock then flowed out in thin, smooth layers that reached far from its source. That's how the mare regions, that cover about 1/6 of the entire lunar surface, were formed. These immense volcanic basins are thought to date back to a period of large and violent impacts from 3 to 4 billion years ago. The materials brought up by these impacts are made up of heavier compounds that would have initially sunk into the magma ocean. Scientists have also detected volcanic residues in recent impacts that have been imaged by LRO cameras. This is the Aristarchus Plateau, with a mysterious channel cut by flowing lava and punctuated by 2 immense craters. One was created by an impact just 450 million years ago. Along its walls are blocks of rock from the lunar crust that fragmented in the impact. Scientists detected volcanic glass-like deposits that are the legacy of ancient eruptions. Then there's the strange landscape of the Tycho crater, from an impact about 100 million years ago. Its central peak, rising 2 kilometers above the crater floor, may be material blasted out by the impact. The same is true for a 120-meter wide boulder that sits on the summit. Around it and on it, scientists see evidence of rock that was melted in the heat of the impact itself. Since its birth, the Moon has exerted a constant and powerful influence on Earth. Gravitational drag from the Moon slows Earth's rotation by 2.3 milliseconds per century, while causing the Moon to drift away at a rate of 3.8 centimeters per year. The Moon's tidal pull acts to stabilize Earth's rotation about its axis, and the tides help promote the formation of ocean currents that shape our climate. To think that the root of this intimate relationship between Earth and the Moon stems from a violent collision so long ago. However, the giant impact theory is not universally accepted. For one thing, there's the issue of water. The dryness of the Moon is consistent with the giant impact theory, which predicts that water and other volatile compounds would have evaporated out of the lunar debris cloud. But the Moon may not be so dry after all. In 1998, the unmanned lunar prospector began an ambitious mission to map the lunar surface with an instrument called a gamma-ray spectrometer. The data showed that hydrogen is spread widely across the poles of the Moon. If it's from ice, millions of tons of water could well be embedded in the soil there. It turns out there are places where water can exist on the Moon, where the sun never shines. Polar craters forever in shadow could shelter significant quantities of ice against solar radiation. Prospecting for ice, the L-Cross probe arrived at the Moon in 2009 aboard the Lunar Reconnaissance Orbiter on a collision course with the 97-kilometer-wide Cabeus crater at the South Pole. Seconds after it slammed into the crater, a trailing probe detected a tenuous cloud rising up from the crater. In the cloud was a mix of carbon monoxide, ammonia, methane, and more. 5.6% of the crater floor is water ice, a higher concentration than some areas on Earth. The presence of water is good news for explorers who dream of one day spending quality time on the Moon. But how did it get there? It might have been delivered by comets striking the Moon over the eons. There's another explanation, one that emerged from rocks gathered by the Apollo astronauts. The samples are graced with tiny glassy globules, minerals melted in the crucible of lunar volcanism. Analyzing these Apollo rocks with new techniques, several teams of scientists have found a compound called hydroxyl. It's H2O with only one H, and could be turned into water, say, for a moon base. Much of what the Moon had was likely lost to space from impacts. Tiny residues might remain in polar craters. The rest, still locked up inside the Moon, might be enough to cover its surface in a layer of water 1 meter deep. Does the presence of water inside the Moon send us back to square one on its formation? It might not, if it had been carried in by comets in the Moon's early days. One new study suggests that the giant impact scenario is more complex than we thought. It holds that another, much smaller body formed alongside the Moon and eventually merged with it. The impact literally rearranged the Moon's interior, pushing molten magma onto the near side, while adding an extra layer of crust to the far side. That explains the lopsided topography of the Moon, the dark lava basins on the near side, and the highlands of the far side. Human geologists with a network of seismographs could confirm this idea. The next best thing is a mission called GRAIL, a pair of spacecraft orbiting the Moon in unison. Such a mission has already performed a kind of planetary CAT scan of Earth. By measuring subtle changes in the distance between the craft, scientists discerned variations in Earth's gravity. The data resulted in a map of groundwater all around the planet. Flying around the Moon, the GRAIL pair could provide new details about the size and composition of the Moon's core, adding support for the giant impact theory, or sending science in a whole new direction. The intimate connection between the Earth and the Moon appears to trace back to their earliest times. If that's true, then the formation of this desolate world can tell us about our own. A blue-green world with a companion reflective enough to light up the night.